Hi, welcome to the second part of the tutorial on multivariate calculus. In the first part, we just reviewed one-dimensional differentiation and integration, and in this video, we're going to talk about higher dimensional derivatives in what's called the denominator layout, which is just a format or notation that people in machine learning at least use. Now, um, in machine learning, we all often see it always being represented as f of x, but it can mean different things in different situations. So let me just make that clear now in these 6 cases. Okay, so for the moment, at least, when I use f of x, I mean that f is a function from reals to reals. In other words, x is just a single variable and f of x is just a single variable. It's a single scalar, right? Now, suppose we go to higher dimensional settings, that could mean different things. Now, one of those things it means is that x is actually a vector which I'm going to represent by x bar, okay, and f is a function that takes a vector and gives out a real number, right? So it takes an n-dimensional vector, gives out a real number. When I use f bar of x, what I mean by that is that f bar is a vector valued output, and it takes in a scale, a scalar variable input. So it takes in a real number and gives out an entire vector. I mean, if you put those two together, of course, f bar of x bar means that it takes in one vector and it spits out another vector, right? So bar basically means either the input's a vector or the output's a vector. When I capitalize it and write capital X, so f of capital X basically means that the input is a matrix, it's an m cross n matrix, and the output is still just a real value. And the last setting is where I write capital F of X, and this in this case means that it takes in a real value and the output is a matrix. Now, as I said earlier, this notation is just really for the next slide to make things a little more explicit. But in machine learning, we often will just write f of x, and maybe it's often understood from the situation what f is and what x is and so on. Are they vectors? Are they matrices involved? And things like that. But for the next slide, at least, it's going to follow this notation. So what is the denominator layout? Let me talk about that in a second. The first case we're looking at is extremely trivial, where f of x, where both are scalars, f prime of x is just a scalar, right? So it's just the derivative is just the slope of the tangent at that particular point x, and that's just a number. Now, when we go to f of x bar, where the input is high dimensional, then the derivative is basically how much does the function f of x, right? So how much does the function f of x change when I vary one of its coordinates? So for example, when I vary x1, or I can ask how much does the function change when I vary x2, and so on, right? Each of them is a valid question. It's a function of several variables. I can ask how much does the function change when I change one of those variables? How much does it change when I change a different variable? Now, that is basically collected together in a vector. So the derivative in higher dimensions of f of x bar is basically a vector. And now we can choose whether to represent that as a column vector or a row vector. Now, just by standard notation that's used in optimization, the gradient is always a column vector. Okay, so this is what we mean by a gradient. You have a real valued function taking in a multivariate input, and this particular function is what's called the gradient, right? And that's always a column vector. So I've written it as the transpose of a row vector at the moment. So that's what we mean the denominator layout. And in some fields, they'll switch the way they do it, and they'll use this as a row and something else as a column and so on. Now the analogous setting is where f bar takes in a single scalar and it outputs an entire vector. That was f bar of x. And here again, when we write df bar of x, we're asking, since the output of f bar is a vector, how much does the first element of the vector change when I change the scalar x? How much does the jth element of that vector change when I change the scalar x? So that's what's written over here. It is the jth element of the vector is how much does f bar's jth element change when I change x. Now this is written as a row vector. F of x bar's gradient is a column vector, and f bar of x has a gradient which is a row vector. This is again just to standardize the notation. There's no reason it has to be like this. You can switch it as long as you switch them all consistently. But this is what's used in machine learning. The next setting is where we have both input as vectors and output as vectors, and in that case, as you might have guessed, the derivative of f bar with respect to x bar is a matrix. It's an n cross m matrix. Now the ijth element of that matrix, aij, just tries to characterize how much does the jth element of f bar change when I change the ith element of x. Right? So that's aij. It's df bar j by dxi. The next setting is where capital X is a matrix and f is just a real valued function acting on that matrix, and the derivative in that case is again a matrix. In this case, it's an m cross n matrix, right? So let's remember over here that in our previous slide we had the notation that was from Rn to Rm, and that's why it's an n cross m matrix. Okay, and you can see that's consistent over here. When you either put n is equal to 1, you'll get a 1 cross m matrix, and when you put m is equal to 1, you'll get an n cross 1 matrix for these two cases. But in this case, df of x by dx is an m cross n matrix, right? Whenever capital X is an m cross n matrix. So of course, n and m are really dependent on what they represent. And here they represented the input and output dimensions. And here the dimensions are m cross n for the input and just 1 for the output. And the derivative is an m cross n matrix A, the same dimensions as x. So remember that over here it's from m cross n to r, and the derivative is basically a matrix A, and the interpretation is aij is how much does that function change when I change the ijth element of the matrix. The last example is where capital F is a matrix valued function, right? So it takes a real value and outputs a matrix, and in this case it outputs an m cross n matrix. And so in this case, capital F of x by dx is reversed, so it's an n cross m matrix. So it produces an m cross n output, but its derivative is an n cross m output. It's a matrix A whose ijth element, aij, is how much does capital F's jith element change when I change x by a small amount. Great. So that's the denominator layout, and it might take a little bit of time to absorb, so I recommend you return to this page at some future point to revise how these things work and what is the gradient of different kinds of functions. And it depends on the input, but at a very high level it's easy to summarize that if you have some dimensions for the input and some dimensions for the output, then the gradient characterizes how much do the corresponding elements of the output change when I change some corresponding elements of the input. That's basically what the gradient should be telling you, and that's what the derivative is. Let's look at some examples. So when f of x is x transpose x, one can calculate that f prime of x, which is the derivative, is 2x. So note that this is a vector. So suppose x is a vector in Rn, then the derivative is a vector in Rn, right? So that's fine. Now suppose that f of x is x transpose ax, where x is an Rn and A is an n cross n matrix, right? Then the derivative is A plus A transpose X. Now remember, both of these are n cross n, right? And this is n by 1. And so the result is basically um, an n by 1, right? So the gradient f prime of x is a column vector. It has n rows and one column, so it's basically a column vector, and that's the notation we'll keep. That is the a real valued function when acting on a vector. If I take the gradient, then it's a column vector. Here's a different example where I've changed what the variable is. Here capital X is the variable, and that's a matrix, and f of capital X is A transpose XA for some fixed A. Over here capital A was fixed and small x is the variable. Here capital X is the variable and small a is fixed, right? And in this case, f prime of x is going to ask how much does f change when the ijth element of x changes. So the derivative has to be a matrix. And what is that matrix? That matrix is AA transpose. Okay. Lastly, let's look at the example where f of x is ax, and this is the case where the input is a vector and the output is a vector of a different dimension. So let's suppose this is an m cross n matrix and x is n cross 1, then the output is m cross 1, right? And A transpose is n cross m, and that's the derivative of Ax with respect to x. It's A transpose. And remember, if m was 1, if m was equal to 1 here, so capital A was just a 1 cross n matrix, and this was just a real valued function, remember that our output would be n cross 1, which is what we wanted. That's exactly in this case, right? So here in here the output is a single real value, the input is n dimensional, and so it would match case 4 if m was 1, right? The dimensions would match case 4 if m was 1, and so the output here is n cross m, which is basically n cross 1 when m is 1. So that's just a way to check that things are consistent between different settings, since 4 has a more general dimension setting than 2. We can set m is equal to 1 in 4 to see whether we're getting the same dimensions as in 2. Now you might ask, okay, can I find some easy way to tell what these derivatives are, right? So maybe x transpose x is easy, because maybe you think of x transpose x as x squared, and you know that the derivative of x squared is 2x. So maybe with an analogy to single univariate derivatives, you would guess what the derivative of x transpose x is. But then how would one guess it for any of the other cases? And here's the hint. The hint comes from the previous tutorials where we looked at inner products, and suppose we defined the inner product between x and a as x transpose a, then we can use this rule that the derivative of x dot a with respect to x is actually a. So this is the rule we are using. And how did we use this rule? Let me give you an example with number 3. So A transpose XA can be is just a number. So A transpose XA is a scalar. A scalar is a 1 cross 1 matrix, right? So it's a 1 cross 1 matrix. A 1 cross 1 matrix has the property that, of course, A transpose XA is exactly the same as trace of A transpose XA. Right, because the trace of a 1 cross 1 matrix is that value itself. Now I can perform trace rotation, right? So I mean, I can do several things actually. Let me take transpose first. So since this is a 1 cross 1 matrix, I can also transpose it and take the trace. If I transposed it, I'd get trace of A transpose X transpose A, right? So that's after taking the transpose. Now let me do trace rotation. I get trace of X transpose AA transpose. And from those of you who remember, the inner product for matrices was basically defined in this fashion, and this can be written as the inner product between the matrix X and the matrix AA transpose. And this is the matrix dot product, which was defined as the dot product between A and B is trace of A transpose B. And so this is basically the standard matrix inner product. And once you've written it like this, you can apply this rule to see that the dot, when I'm differentiating a dot product with one of those variables, I get back what's on the other half of the bracket, right? And that happened over here too, actually. Over here too, I was looking at the dot product between X and X. That's exactly X transpose X, and the derivative is 2x, right? So that's the 2 happens because I need to apply the product rule, and the first time I take a derivative with respect to one of them, I get x, and the next time I take a derivative with the other one of them, I get x. So that's why I get 2x. So I get 2x over here because I'm applying this rule as well as the product rule to differentiate with between both of them separately, right? And actually that's what I'm doing in all of these cases. In AX, I can actually write that as the as A transpose X, right? So that's in some sense says that if I differentiate with respect to X, I'm going to get A transpose. Yeah, so that's kind of a common theme here, that if I write something as, whatever transpose X, or remember X transpose whatever, then the derivative with respect to X is going to be whatever remains. It's going to be A transpose. Great. That's all for now for higher dimensional derivatives. Next time, let's talk about higher dimensional integrals.